We continue the lecture on the models of network formations on slide 75. And so we have been discussing the price model, and now we are going to see some mathematical derivations. The final conclusion is going to be that indeed by using this procedure we are getting a network at the end which will have a power law degree distribution. Okay, in order to see this kind of mathematical description and derivation, let's consider the following. So with qi or q sub I, we are going to denote the in-degree of vertex I. And with pqn, we are going to denote the fraction of vertices in the network which have in-degree equal to q, where the network contains n vertices. So by the way, the network which we are going to consider is going to be, of course, a growing network. Okay, so when it has n vertices, then the fraction of the total number of nodes which has in-degree equal to q is denoted by pqn. And by this one, the probability that the citation, the given citation, is referenced to a particular other vertex I is of course proportional to qi plus a. So qi was the in-degree of vertex I, and of course this plus a is given there because that's the number of free citations as we fixed this just in the previous slide, I guess. So there is a normalized version of this expression here, so qi plus a, which looks like this. So what does it mean? That we are normalizing the qi plus a, so the probability that a particular vertex gets the citation, it's normalized by the total in-degree of all these vertices. Okay, so the total in-degree. Now if we do the summation, now of course this could be done independently. We have n nodes, so I goes from 1 to n. So sum of the qi is equal to n times q with this brackets, whatever bracket, and as you might remember, the why we can write this. This is a reminder here that the first moment of q, which is now the in-degree, can be expressed in this way, because this is basically the average in-degree. Okay, and so hence we get back so n times n minus n to the power of minus 1, of course it's equal to 0, so we get back the sum of qi. Okay, plus n times a, which is of course just a taken n times. And so the average degree is in fact also denoted by c, according to our earlier notions in the previous lectures. So we can just write the equation in this way. Okay, now based on this one, the expected number of new citations to all vertices with degree equal to q is equal to this expression here. Now you can see that n times pqn is going to be the number of the nodes which has degree equal to q. Okay, why? Because pqn was the fraction of these vertices, so divided by n. So if I multiply it with n, then I get the number of them, okay, together. So not n, not pqn, but multiplied together. We said that the new paper contains c new citations on average. Okay, so that's going to be this factor, and this expression here is the probability that a particular node is getting that citation, as we derived it in the previous slide. So the formula expresses, so it talks about those vertices which already has q citations. And so based on this simple formula where n is actually gets simplified out, we can use the so-called master equation technique for the evolution. So the procedure in which we can observe how the network is changing. And in this master equation, what we are going to do, okay, let me jump to the next slide, and then we can get back to it. So what we are going to do is we are going to model what's happening when a new node is joining to the network. And if a new node joins to the network, so a new paper appears in the citation network, then it's going to reference on average c other number of previously published papers, and by that one those papers which are getting cited by this new one, their in degree is actually going to be increased. Then so there will be some, so, and by that decreasement, basically some of the nodes will have so previously those which had let's say k minus 1, so let's say five citations, then those which get new citations, they will have 6 citations. Okay, so then they are going to be located in another group because seemingly, okay, now getting back here again to the first slide, seemingly we are collecting the nodes into different groups according to their in degree. Okay, so this is going to be the procedure that we are going to have some vertices which are going out from this group or leaving this group of a certain number of citations. There will be some nodes which are entering this group, and then there will be some nodes which are remaining there. Okay, right. So when, and this is written here. Okay, so when we are adding new vertex to the network, then we will have n+1 nodes, of course, and so the nodes with in degree q increases by 1 for every vertex, and those yeah, so whatever I said, I get confused here now. Whatever I said before, it's written down here. Okay, so the number of the expected number of such vertices which had earlier q minus 1 in degrees, so q minus 1 number of citations, then now with this addition, some of them will be having q citations. Okay, so we know from the previous slide that the number of them is equal to this expression. Okay, just get back here. And oh, sorry, just get back here, and then you will see. Right, so some of the vertices which had earlier q in degree, then when they get a new citation, then they will have q+1 in degree. So the expected number of such vertices are equal to this expression here. Okay, so again, these two are based on the previous discussions. And the number of vertices with in degree equal to q in the network after the addition of the single vertex is n+1 times pq n+1, of course, by definition. And which if we put together all these three components, then this is the number of nodes with in degree equal to q in this new network, so with n+1 nodes, and this was the number of them before. These are the number of them which we gained right now. So those which had earlier q-1, but now they have q many citations, and these are the nodes which we lose basically in some sense from this group of in degree equal to q. So this is with minus, because these nodes, they had q many citations, and now they have q plus 1. Okay. Now q equal to 0 is a special case, and it's written here. So some part of the equation gets simplified. So it's basically it's here, instead of this complicated one, we have only 1 here as a number. All the rest is the same. Okay. So now we can consider the case when n tends to be to infinity. Okay. So the network grows to infinity. Then it turns out that the formula, the two of them, so the special case when p, so the q is equal to 0, and when q is larger than or equal to 1, they get the form of these two equations here. Okay, so now this one is the simplified version, or the nicer version of the formula from the previous slide. And without giving the full details, if we are rearranging these two formulas, then we get for P0 we get this kind, and for PQ we will get this nice one here. Okay, so Q is the in degree which we are considering. A is the number of free citations. Okay, so it's every node gets automatically that many citations, and C was the average out degree of a node. Okay, so we know almost everything here. Now let's see, I'm just repeating here the two equations, and so if P0 is given, then we can start computing P1, P2, P3, and so on. Okay, so with iteration. And it turns out that PQ can also be written in this way, in which now we don't have this recurrent formula as here, or iterative version as here, but instead in this formula now, which looks more complicated than it is actually. Now in this one we only have Q, A, and C, so all the values which we know beforehand. Okay. Furthermore, so please don't get that. So please, yeah, just take it easy. It's just it looks bad, but it's not that difficult here. And I'm not. We don't need to do the full details here. Okay, it's just getting the grasp of it. So we can use the gamma function, which is defined by this strange equation here, or integral here, and you might know the gamma function because it's the continuous version of the factorial function. So for this function in particularly, it holds that gamma at x plus 1 is equal to x times gamma x. Okay. And it has also gamma x plus n divided by gamma x is just this multiplication here. So it turns out that after doing some tricks, PQ can be written in this way here, now using the gamma function. Okay. Furthermore, there is another famous function which is called Euler's beta function, which is composed by the gamma functions. So you can see here that this guy here, so this expression here appears in the previous slide basically. So gamma, gamma, and gamma, gamma. Okay, so it turns out that that PQ can be also written with in terms of the Euler beta function, and you can see that. So the thing here is that, so the point here is that here what we can see in the upper part of the fraction, now that one depends on Q. What is down here below, it doesn't depend on Q. So basically this part here is just a constant value. So we need to understand the property or the characteristics of this function here above. Now there is a nice approximation for the beta function, which is again gives us back the gamma function, using which we can write this form here, and it turns out then if q is much larger than a, then PQ is basically ordo, if you want, ordo q to the power of minus alpha. And I mean this alpha is related to, of course, to this expression here. So having said all these, the conclusion is that we get a power law degree distribution function. Okay.